BYD DM EV-based hybrids, DMI, DMP, DMO, as in the BYD Shark, Sealions, Seals and Dynasty models, Denza Z, Z9, B5, B8, Type 7, Type 3 and more. This world's most successful PHEV technology is central to BYD, world's largest EV and PHEV brand, being able to target becoming the world's largest automotive brand overall. The tech is reshaping the great pivot of the entire automobile industry and the future of all vehicles that incorporate combustion power. Welcome to One Finite Planet, a channel on our journey to a new age, today focusing on the tech behind BYD DM technology, with other videos linked in the description focused on how this technology is transforming the entire car industry. Chapters 1. There are two fundamentally different types of plug-in hybrids, with surprisingly different characteristics and success rates, plus the limitations of combustion-based P2 plug-in hybrids. 2. EV-based hybrid advantages: cost, simplicity, reliability, power, EV mode and shared production facilities. Then breaking the ICE thinking, how EV genset engines are so different from normal car engines. No, the generator doesn't only charge the battery. Peak power versus haulage and towing limitations and the clutch bypass, and then making sense of the specs, how to tell the two PHEV types apart. Then a short section on driving and how the modes actually work. So first, there's two entirely different types of plug-in hybrids. They start from different base vehicles and they're designed to solve different problems. The first type, combustion engine based, where the goal is to improve fuel economy and reduce emissions. Then EV based, where the goal is to reduce the need for charging and reliance on charging infrastructure. Both have combustion engines and electric motors, but they need very different combustion engines, and the electric motors are doing a very different job. And see what's behind BYD's ominous growth and other content linked below for details, but BYD switching between the two types has played a pivotal role in BYD's history. BYD was first to add a generator, or technically a genset because the generator is just the electric part, to an EV to create the F3DM in 2008 as the world's first modern production plug-in hybrid. But like all the first wave that followed, perhaps except the Mitsubishi Outlander, it failed commercially. As shown on the graph, they reached just over 1,000 a year before DM 2.0 and a switch to the combustion engine-based hybrid, which saw a 14 times jump of sales in 1 year, as shown here, before settling to, on average, around 70,000 per year, until the fourth generation, DM 4.0 or DMI and DMP, in 2000, when they switched back to the taken EV and added genset approach, but this time with enough experience in EVs and better battery tech getting it right, and the sales heading to millions per year. Early on, batteries were too expensive and car makers didn't have enough experience making EVs. The lesson is, bad EV-based hybrids suck and good ones change the world. In just 5 years, BYD went from 17th in China to becoming a contender for the world's largest car brand. In summary, first generation DM was EV plus genset technology. DM2 and DM3 were PHEVs based on combustion engine vehicle technology. But DM4 and beyond are all DMI, central to BYD's ominous growth. They're all EV plus genset based hybrids, with the change from first gen DM being using BYD's vastly improved and lower cost batteries and BYD's, by that time, extensive experience with production EVs. DMP, this is a derivative of DMI with the addition of one or more rear electric motors. Note that while DMP badge always indicates all-wheel drive, BYD's been inconsistent in adding the DMP branding to all all-wheel drive models, so some are just branded DMI. DMO, these are again so far all-wheel drive, but with the engine bay power unit in the north-south orientation for installation in ladder frame vehicles. Covering first the PHEV type most of us are most familiar with, There are lots of brands in the market, particularly Volvo, BM, Audi, Mercedes, BMW, Porsche, etc. We call them just PHEVs, and they're effectively just electrified versions of the combustion engine technology we've known for over a century. The industry term is P2, or sandwich hybrids, because the main electrification is to add what's labelled a P2 motor sandwiched between the engine and the gearbox. Note that Toyota power split hybrids are different, and they're great hybrids, but not well suited for plug-in vehicles for reasons outlined in content linked in the description. For traditional brands, P2 hybrids build on the decades of technology from building combustion engine vehicles and allow capitalising on and extending the life of decades of engine development. No need to first be an EV expert before you start. It's the straightforward way to get a plug-in hybrid. And, as outlined in content on the Great Pivot, are seen as just stepping stones anyway. They're an easy way to take a base vehicle, add an extra 100 horsepower and create a stoplight rocket. This technology is at its best when it's used for cars where performance alone is the absolute priority. But instead of starting with a much simpler EV, this is starting with a more complex vehicle and then making it even more complex, heavier, less reliable and more costly. And in the role of a plug-in hybrid, there's another big problem, because a key goal is to offer an EV mode. If all the power is coming from gasoline, you can generate electrical power. But if you're running on just electrical power, that means you have no access to what in these vehicles is the main power source, that asset of the combustion engine. EV mode means running only on the secondary power, and that leaves them relatively underpowered. It makes EV mode, that's fine for special zero emission zones where you're going to drive slowly or for not waking the neighbours, but if the goal is to allow everyday driving in EV mode, it means either switching from stoplight rocket to a heavy, seriously underpowered slowpoke, or frequently firing up that main combustion engine to boost power, which is inefficient as fuel is wasted warming up the engine and cold start pollution means emissions are high. These, sometimes called parallel hybrid PHEVs, and criticised as worst of both worlds, had some of their success as a result of effectively gaming many regulations and tax breaks, particularly in the EU. But for nearly a decade, these made up over 90% of PHEVs and were so dominant in most markets that people think of these as the only plug-in hybrids or PHEVs, which gives plug-in hybrids a bad name. And if you hear plug-ins are out of favour and being dropped as tax loopholes close and standards end their viability, while it is true for this type of PHEV, it's not true for PHEVs overall. That's because there's another type, where the design is take an EV and add a generator/genset where the frunk would be. And yes, the first ones effectively went wrong, because if at first you don't succeed, you're doing about average. But it was also some politics, a bit of a holy war. All the first ones had clutch bypass, and most still do, which today stops them being called EREVs, which is a label initially brought to prominence by General Motors for the Volt, which had a clutch bypass, but was ultimately ruled as not an extended range electric vehicle by the only formal body I'm aware of officially defining what the name means, CARB, the California Air Resources Board. Not because these vehicles weren't good enough as an EV, but because they were too good in combustion engine powered mode to not only satisfy EV purists in a holy war, but also qualify for EV subsidies, which they didn't want to waste on people who might drive them on gasoline power. In fact, the only vehicle to ever qualify was a special version of the BMW i3 that was set to only allow people to use 1.9 gallons of its 2.4 gallon fuel tank. Another name people apply is series hybrids, but as explained in content linked in the description, in reality all hybrid cars have elements of both series and parallel. Series hybrids really applies properly to ships, locomotives and tanks, etc., where the battery is not a source of traction power because as soon as it's used for traction power, it's a parallel source of power. I call them generator-equipped EVs or GEVs when trying to specifically differentiate them without a full description, but they're becoming so dominant that in China now, people just call them hybrids and that's enough. Yes, at first they didn't succeed, but once you get it right, this is the simplest, most cost-effective and most reliable way to make a plug-in hybrid, which is what has enabled for them to already become the most common PHEV type worldwide. Most are in China, so only smaller numbers have reached the rest of the world. If you look at the results since 2020, when BYD made the switch to this type of plug-in hybrid, you can see their sales have taken off even faster than BYD's EV sales. The result is that now most plug-in hybrids worldwide are actually of this type, but most people outside China have seen far less of them. While adding a battery and a motor to a combustion engine vehicle increases cost and weight and results in poor performance in EV mode, adding a range extender to an EV can reduce battery size, which saves weight and cost, and can more than offset the weight of the range extender engine, which can weigh as little as 85 kilograms and cost as little as $600. So overall, most often you get a lower price, lighter vehicle when converting an EV into a plug-in hybrid. And in this case, EV mode's fine. And while now it's the combustion power mode that has poor performance, by ensuring the battery is always kept sufficiently charged, there's no delay and no emissions starting up the electric motor to contribute. So there's no negative impact. But all the technology that's been used to produce engines with broad power and drivability no longer matters. Instead, you have these Atkinson cycle engines that can be kept within a narrow power band, resulting in simpler designs and greater thermal efficiency when the engine is in their secondary role rather than being the main always used source of power. But to understand them, you've got to break the ICE thinking shaped by a century of internal combustion engines. There are two power sources, the combustion engine and the battery, not the combustion engine and the motors. It's easy to fall into the trap of trying to equate everything to a combustion engine car and to consider the equivalence one-for-one replacement where the fuel tank is replaced by the battery, the engine is replaced by electric motors, and the gearbox is replaced by nothing. But once you consider the function, the logic, it becomes easier to understand, where the first function is storing the chemicals that hold the energy, which is the fuel tank or the battery. Then the next is the place where the chemical reactions turn energy into kilowatts, which is the engine, but again, it's the battery. Then what takes the kilowatts and use it to turn the wheels, which is the gearbox or the electric motor. The best way to think of electric motors is like the transmission for electric power. Electric motors aren't a source of power. Think of an electric fan at home. You know it wouldn't work without a power source. You could run it from a generator or genset, or from a battery, or plugging it in. But it can't itself be a source of power. Next is understanding that the engine in an EV-based hybrid doesn't have the same function, the same design, the same cost, or the same weight as a traditional car engine. As covered, they can cost as little as $600 and weigh as little as 85 kilograms because they don't have to deal with low-down torque, the big stresses. The engine only has to operate well within a very specific RPM band and a very specific load band. For a car engine, maximum overall efficiency is best efficiency across all loads and scenarios. It's a huge engineering challenge and companies have made huge investments to solve it. For a generator engine, designers need never deal with low loads. Load too low? Use battery power until charge drops. Then use the combined load of powering the motors and at the same time charging the battery to move the load into the ideal range, and do that until there's a surplus of battery power, and then you can drop onto using just the battery for a time. High loads for rapid acceleration? How can you match electric power? Yes, in most BYD vehicles, under the right conditions, mechanical drive from the genset engine is used to drive the vehicle, but they can only do it under just the right conditions. It's sort of like the difference between my being able to order the odd dish in an Italian restaurant and use Italian under the right conditions and saying I can speak Italian. Under most conditions that you encounter, these engines are unable to drive the vehicle, other than by the path of generating electricity that goes to the electric motors. And the next point is that generator, driven by the genset engine, is not only used to charge the batteries. Many get it wrong, but here for once is an example of it being explained correctly.
It is an engine, but they'll call it a range extender. It basically makes electricity for the electric motors.
The main role of the generator is to send power to the electric motors, to the wheels, with, under some conditions, excess power also being used to top up the battery, but not all the time. In fact, for the fastest acceleration, you need power coming out of the battery, joining with the power from the generator, so that both combined go to the electric motors. And that's how the vehicles produce their full power. It's not from the battery alone, and it's not from mechanical power joined with electric power, which is just as well, considering it isn't even possible most times when you want full power, because at less than 70 or 80 kilometres an hour, there's no mechanical connection to the wheels possible. The reality is, like every other device that operates while being charged, laptop, phone, EV battery, it's operating on power from the charger while it's being charged. Part of the problem comes from the series hybrid label, but think in terms of a 12-volt battery in your car. The alternator supplies voltage, and when it's more than the voltage in the battery, it goes into the battery. It's going into the battery and charging it, as well as providing the power for the rest of the car. When the alternator voltage drops, then the voltage from the battery takes over and the power is coming out of the battery. But current can't go both in and out of the terminal at the same time. But how hybrids work is a bit of a trade-off, and the key to it is that peak power is normally much more than constant power. And the sportier the vehicle, the more peak power is only ever available for a very short period of time. Consider the Model S Plaid. It's got a 95 kilowatt hour battery, but can draw up to 760 kilowatts of power, which means it can only supply that peak power for 7.5 minutes. The BYD Shark battery power can only supply peak power for 9.5 more minutes. And even pure combustion engine sports car, like the Cayenne Turbo S, when you calculate its peak power and the energy in its fuel tank, it can only deliver peak power for 15 to 20 minutes. And how quickly you can burn through an entire fuel tank is a reality people come face to face with when driving at really high speeds on a German autobahn. And the hybrid is designed around the fact that the normal continuous power requirement at most realistic speeds is far, far lower. So the combustion engine is designed to have the ideal efficiency in the band of the speeds that will be continuously required. Short bursts of high speed, you don't want to design the engine around those, or it'll be less efficient in normal use. And the fact that it can be designed around a much lower power requirement, and then the more powerful electric motor come in and boost the energy levels for the shorter period of time that the peak is needed, is a key to how these things work and how these engines can be so efficient in this narrow band. Now consider another example of super efficiency. Large container ships or tankers that travel at sea. They always operate within their peak load. If conditions force them to go a bit slower under that peak load, they travel a bit slower. They're not designed to be able to deliver short bursts of high speed like a car can, and the result is their engines are far more efficient than any engine available in a car, and they don't need a hybrid to cover the boost because there is no peak demand. The genset engine can be designed for that same efficiency, hauling the vehicle along the highway. But in this case, it has the electric motors that can deliver that peak power on demand when needed for sporty driving. The first implication? For long distance haulage, in situations where there's no need for sporty, rapid acceleration, adding the electric hybrid system is of little value if all trips are long distance. Hybrids don't really help solve that problem. The second implication is that for towing heavy or high air resistant loads over long distances. With a plug-in hybrid, you design the engine for the sustained power, But recall from the chapter on genset engines how they're designed to meet only continuous average power. What you'd expect to sustain up to perhaps 140 kilometres an hour. Adding a trailer is like converting the vehicle into a larger long-haul vehicle that requires more power. Sportiness is again not expected, but load at any given speed is higher. Just going slower can adjust for a certain amount of extra load, but when the combined vehicle can more than double the load? Now, the key advantage of gasoline or diesel for energy storage is gravimetric energy density of 12,000 watt-hours per kilogram, which is 60 times that of LFP batteries that are around 200 watt-hours per kilogram. So it's easy to carry enough liquid fuel for a very long range, but not easy to have enough electric power to continuously provide for significant additional battery power over a long range. That's more for those short bursts. The result is the most efficient vehicle for long-distance heavy towing needs a more powerful genset engine that uses more fuel than the most efficient engine designed for when not towing. So catering for towing can force a compromise. And the second point is on the clutch bypass. Recall how, for highway driving on gasoline power, the genset engine is like that of a freight vehicle, producing the power required to maintain speed. Operating in that zone where the combustion engine is continuously running in its most efficient zone, just like a freight vehicle, the hybrid system itself is no longer helping. And that's where the clutch bypass comes in. Under those conditions, you just don't need to turn the energy from mechanical power into electrical power and then back into mechanical power again. There are losses in the process, which could make a vehicle of this type less efficient than a regular hybrid under these conditions where mechanical drive is used to drive the wheels. And that's why there's a clutch bypass on models like the BYD, to cut out those conversion losses. Now, the conversion losses are becoming less significant as electric motors, generators and inverters become more and more efficient. And the range in pure electric mode gets so big that people care less about that last bit of efficiency when extending range using gasoline. But that's if you're only using the hybrid mode to extend range. Effectively as insurance against rare occasions when charging becomes impractical. And because it won't be used often, the ultimate efficiency when extending range doesn't matter. But if the vehicle might be used as a hybrid for extended periods of time because, for example, there's a period of time when charging at home might be impractical, then for that use case, for the ultimate efficiency, you need that clutch bypass. It's only going to operate when the load is within those parameters that allow the engine to remain within its perfect power and load band. But that's a key difference between a range extender and an engine with a clutch bypass. The engine with a clutch bypass can do everything a range extender can do, but it can also offer full efficiency as a hybrid if it's operated for periods of time without electric power. The next point to understand is C-rates. The idea that the battery, as we've covered already, the battery is doing some of the functions of an engine, which means for the same technology, the bigger the battery, the more power it's producing in its role as an engine. Think of a AA battery. Add two AA batteries, you double the power. Put them in series and you double the voltage. Put them in parallel and you double the current, but either way you double the power. When they're in parallel, it's exactly the same as having one bigger cell. No matter how you add more battery capacity, the result is the same, more power. Now the C rate for a technology is the same no matter how big the battery is, where the C rate reflects the charge time of the battery. A C rate of 1 means it takes 1 hour to charge. A C rate of 2 means it just takes half an hour to charge. So you divide an hour by the C rate and you get how long to charge the battery. Charge one AA battery or two AA batteries, you can charge them in the same time. They're both the same C rate no matter how much battery you've got. But the power to charge two batteries in the same time is double the power to charge one battery. So a 1C 60 kilowatt hour battery to charge in 1 hour will require a charge rate of 60 kilowatts. A 120 kilowatt hour battery to charge in 1 hour will require a charge rate of 120 kilowatt hours. 2C batteries of the same size would require 120 or 240 kilowatt hours to charge in half an hour. And there are also C rates for discharge. The power a battery can deliver for the same chemistry is also determined by its size. So if we go back to that Tesla Model S Plaid, which if it was delivering full power would fully discharge its battery in 7.5 minutes or 1/8 of an hour, that battery must have an 8C discharge rate to be able to deliver that much power. That's how it works. And that brings us to the last subject, making sense of PHEV specs and how to tell PHEV types apart. The key is in the motor specifications. The first thing is for an EV-based PHEV, full power comes entirely via the motor. But there's a slight complication in that isn't always clear from the specifications. Consider these BYD Seal 6 specification. The two versions available in Australia both have a combustion engine rated at 72 kilowatts to power the genset, which combines with either a 10 kilowatt hour battery or a 19 kilowatt hour battery, with a quoted traction motor maximum of 120 kilowatts or 160 kilowatts. So a starting point would be that almost doubling the battery size only adds 40 kilowatts of power, which means without any battery power, you're going to get around 80 kilowatts, not far off the 72 kilowatts from the combustion engine. So a 10 kilowatt hour battery producing around 40 kilowatts of power is not that far off. And then a 19 kilowatt hour battery producing around 80 kilowatts of power being added to the 72 kilowatts, again, not that far off, but the battery at its maximum has to be able to deliver a little bit more than that for the figures to match up. But then we've got the other strange figure, that the quoted maximum is actually slightly higher than the quoted traction motor maximum. And the secret to this is a traction motor maximum output is called an S2 specification, and there are tests that require it to deliver that power typically for around up to 60 seconds, which is way longer than the maximum power to accelerate the vehicle from 0 to 100. And over a shorter time, the power is slightly higher, but it's still all coming from the electric motor. Another secret here can be read from the details on the motor. We've got a TZ210XYB and a TZ210XYC. Only one letter difference between these seemingly quite different motors. And in fact, the 210 is the stator core or outside casing diameter. Physically, these two motors are going to be the same size. They could technically use different electrical windings or different quality magnets, but overall, when you look at the cost savings that can generate, it quite often isn't worth it. The main difference is very often just how the controller is programmed, because what the electric motor draws from its source has to not overly stress the battery. If you took the same power out of the 10 kilowatt hour battery as you draw out of the 19 kilowatt hour battery, you'd really stress that battery and give it a very short life. So you have to configure the motor for lower power, even if you find it's physically the same. And in another vehicle, the Z9 GT, where I've seen a teardown of both the EV version and the PHEV version. Once again, a motor with just one letter difference at the end is rated at either 330 kilowatt hours or 220 kilowatt hours. The motors actually have the same weight as well as the same other dimensions, which means the motors, windings and silicon carbide components are pretty much guaranteed to be exactly the same in the two. And all it comes down to is how the motor's programmed. So what this all means is when looking at the specifications, allow for the fact that the quoted maximum can be slightly higher than the motor's quoted maximum, but that doesn't mean the power is coming from anywhere else. It's still coming from the motor for a very short period of time required for that maximum. But if the motor maximum is around half or less of the vehicle's total, then it's going to be a combustion engine plug-in hybrid. And the motor is typically rated even less than half. So that's it for the key points, but just a quick summary of what happens when driving. First off, full power requires the combustion engine, not just the battery. And it's misunderstood, as this quote demonstrates even by those enthusiasts about the brand. If, when the driver demands the extra power, it came in only mechanically to the wheels, it would mean that power could only join in at about 70 or 80 kilometres per hour. Not very helpful in a 0 to 100 sprint. But perhaps even more significantly, in a four-wheel drive vehicle like that, where battery power would be going to both front and rear motors, and suddenly you're sending all the mechanical power just to the front wheels, which would suddenly see this huge surge of torque that would break traction. It just would be impractical. The reality is that when you're in full power, the bypass clutch is never used to mechanically deliver power to the wheels. The vehicle never switches mode from generator power to mechanical power while at full power. It can switch the other way around when full power is required, but it won't switch to mechanical power to deliver full power. It would be extremely problematic. So the next point in driving is there are effectively two situations, and they're determined by the fact that the battery has a floor level, a state of charge which is to be maintained by the car. It typically defaults to around 20%, but you can set it up to as high as 80%. So the car will prioritise electric power, or if in EV mode, only use electric power until the state of charge falls to that threshold level. If you're in hybrid mode and you demand the extra power, then the generator motor will activate and provide the extra electric power. But normal driving above the battery floor threshold will be on electric power. But once you fall to that floor threshold, you're in sustained charge mode, where the car drives like a non-plug-in hybrid. And as covered before, on the highway, at typical highway speeds, the combustion engine will be just continually running. It's in its perfect power band, and if it's within the speed range, the clutch bypass will be activated to avoid those losses in what's called the double conversion tax. And the car will be just continually running on combustion power. But in the city, in stop-start traffic, you're going to sometimes stop. When you stop, you're going to turn off the combustion engine. And the average load at city speeds is outside the efficiency band of that combustion engine anyway. So you don't want the combustion engine on all the time. You want to sometimes be using battery power even when you're at that floor level, and then bringing in the combustion engine to power the car, but using the extra load of the charge on the battery to give the engine sufficient load to operate in its most efficient range. Once that power that's in excess of what's needed to drive the car has charged the battery enough to build the buffer a little bit above what's needed, the engine can switch off, possibly when the car next stops, and left off for a period of time. So you have this pattern at sustained mode where even then, some of the time, the combustion engine isn't being used at all, it's just using battery power, and it is charging up a bit and dropping down a bit. And because the engine's not needed absolutely suddenly, it's not an emergency calling for the engine. Even when peak power is required, the battery can deliver way beyond its normal power for a very short period of time while the combustion engine fires up, warms up a bit, and then is given the load of the generator to help with the supply of electricity for the motors. So the engine is not placed in this stress, it never has to deliver torque low down, it never has to deliver full power while completely cold, and overall, the car is just more efficient. So that's it for this summary of DM technology. Hope it helps. If it did, please like and subscribe.